Let's now talk about theta notation. Theta notation is used to represent exact bound of a function or an algorithm or program. Whenever you know the exact bound, prefer to use theta notation. It gives you the best information. It tells you that's what the order of growth is, right? When you use big O notation, it means either exact or an upper bound. So we use big O notation only when we have an upper bound. When we have exact bound, why not to use theta notation, which gives better information. Omega notation is used to represent a lower bound. So when you have a lower bound, then you use omega notation. Theta is used when you have exact bound on order of growth. Let's see the mathematical definition. We say Fn is theta of Gn if and only if there exist two constants C1, C2 such that C1 is greater than 0, C2 is greater than 0. So if you see, compare this theta notation definition with big O notation, omega notation, it's a combination of both the definitions. In big O notation, we were bounding from this side. In the omega notation, we were bounding from this side, right? And there was one constant in both of them. Since we are combining those two, we have two constants C1 and C2 now. And here also we talk about all values of n greater than n naught, where n naught is greater than or equal to 0. We talk about only this quadrant of the 2D coordinate system, right? N naught greater than 0, equal to 0. And these function values are also greater than equal to 0 because they represent time taken by an algorithm. So theta notation definition of a function bounds the function from lower side and upper side both. For example, if you see this function 2n plus 3, this is the line that represents this function, right? We have seen this in big O notation, right? We found the constant as 3, and we have seen this in omega notation, we found the constant as 1. So in theta notation, we bound the function from both the sides. And bounding the function from both the sides is only possible when you have the same order of growth, right? Because the order of growth is different, then you can't bound it from the other side. Because when n tends to infinite, we talk about n tends to infinite, we'll see the differences. We would not be able to bound both the sides. We will be able to bound only from one side, right? Both side bounding is possible only when your function fn and gn, they have same order of growth, which means the highest growing term is having the same order of growth in both the expressions. Let's see an example. Fn is 2n plus 3. I've taken the same example here, and the same reason we discussed in omega notation. We just take the smaller value constant, right? The smaller value constant of the highest growing term, and is the this 2n is the highest growing term. We have 2, so we take 1. And for C2 we take 3, right? C2 belongs to the theta notation constant and C1 belongs to the omega notation constant, right? So we take 1 and 3, and now we try to figure out n naught. So we have this inequality, right? 2n plus 3 should be is greater than equal to n and should be smaller than equal to 3n. From this inequality, this part of the inequality, we get n greater than equal to 3. From this part, we get n greater than equal to 0. See, we actually get n greater than equal to minus 3, but we talk about n not greater than equal to 0 only. So we consider n as greater than equal to 0, right? Now, if I take a combination of these two, for which values of n the both will be true. So this is true for n greater than equal to 0. This is true for n greater than equal to 3. They both will be true for n greater than equal to 3. So we have n naught as 3. So we have C1, we have C2, we have n naught. That's why we say it's theta of n. We can use direct method also to find theta notation of an expression. For example, if I have this complex expression, I don't have to find out C1, C2 and n naught. I can use the same method that we discussed in order of growth, because this method gives you order of growth and theta notation represents the exact order of growth. So what is order of growth of this? We have discussed it multiple times. We ignore the lower order terms. We ignore this constant and we get n square as order of growth. We can simply put it in theta notation. It's theta n square. Here we can ignore the lower order terms. We can ignore this constant and we can say it's theta of n cube. That's the order of growth of this, and we can simply put order of growth in theta. Here we have log n and n, so this is lower order term. We ignore the constant and we get the order of growth as theta of n, right? So you can use simple order of growth to get the theta notation, and we can use the same for big O and omega notations also. Let's now see some interesting facts about theta notation. The first fact is, if Fn is theta of Gn, it means Fn can be written as big O of Gn also, big omega of Gn also, right? And Gn can be written as big O of Fn and big omega of Fn. For example, if fn is 2n square plus n, we can write it as theta n square. And we can also write it as big O of n square, we can also write it as big omega of n square. And similarly, n square can be written as big O of 2n square plus n. Now you might be wondering, what is this big O of 2n square plus n? See, when we write a complex expression in big O notation, this complex expression is actually equivalent to big O of n square only, right? Because again, you can ignore the lower order terms, you can ignore the constant of the leading term, and you can again write it as big O of n square. So you can have complex things inside big O notation or big omega notation, and again the same rules apply, and you can simplify those complex terms, right? So since theta represents exact bound, all these four things are true when fn is theta of gn. They both have exact order of growth, right? Fn and gn, and you can write both of them in all different other four ways. The next thing about theta notation is it represents exact bound, and this is why it is super useful. Whenever you have an algorithm and you know the exact bound, you should always use theta notation. For example, if you talk about maximum in an array, you will always have to traverse through the array. You know that this algorithm is always going to take theta n time. It's good to use theta notation here. If you say big O of n, that kind of does not give you the complete information. It can be n or can be less than n. But if you know it's always n, it's always linear, why not to use theta notation? Similarly, minimum in an array, sum of an array. Even when your algorithm has different time complexities in different cases, it's better to use theta notation. For example, if you talk about insertion sort takes a linear time when your array is sorted, and it takes a quadratic time when array is not when array is reverse sorted. So it's better to say in the best case insertion sort takes theta n time, because you know it's linear, right? It's not more, not less, it's exactly linear for insertion sort in the best case. And better to say insertion sort in the worst case takes theta n square time, rather than saying insertion sort takes big O of n square in the worst case. Better to use theta notation, because when you know for sure that this is exactly n square, use theta notation. Also, if you want to talk about time complexity of insertion sort in one line, then you can say insertion sort is big O of n square. Here you can use big O notation, because when you say big O of n square, it covers the best case, covers the worst case. You are saying it is either n square or less than n square, which covers both the cases. Now, taking examples of theta notation. So all the constant values, they are theta 1, right? No other values. Theta means exact order of growth, right? So we can't have anything else like we had in big O and omega notations. We had sometimes unions of certain things, but we have exact sets here. So if you see this set, this has the leading term as linear, right? This is linear, log n is lower growing. This is also linear, so we can say it's theta n. Here, exact order of growth is n square. So we say all these things, this both things, they have theta n square order of growth. Theta n square means the highest growing term has to be n square, not more, not less.